Hello everyone. So the GATE exam is over. Quite a good number of questions came on digital and microprocessors. So in this presentation, I would like to give the solutions to those problems, discussing its corresponding fundamentals. Some 5 questions have come combinedly from digital and microprocessor. They are not very hard to answer, but you need to have very clarity in the concepts. Then only we can answer without any doubt. Let me explain what are the solutions to each problem. So the first one is based on a simple sequential circuit like this. One JK flip-flop and T flip-flop are given here, and then it's asking, with the initial state given, what are the sequence of states it is going to perform. Okay, it is going to count. Whenever you want to analyze this type of circuit, we have to rely on the table which consists of present state, flip-flop inputs and next state. By the way, what are the flip-flop inputs here? It is given as JA expression is given, KA expression is given and TB expression is also given. So, if you look at the solution, I have to say like this one. Ka is A plus B and the TB is A. So, this is the given information. Using this one, I have to find out how the counting takes place. Right. So, whenever you want to go for analysis of any circuit, I am going to write like this one. So, to analyze the given circuit, we have to use this type of table having present state, flip-flop inputs and next state. For this, we require knowledge of the JK flip-flop truth table as well the T flip-flop truth table. Using that, from the present state information, I can find out what is the next state. One more time I tell, JA is given as this, A bar plus B bar, and JKA is given as A plus B and the TB is given as A. So, from the previous circuit, we can make a note of this one here. So, now for each present state, we have to find out its flip-flop inputs, and using the truth table of JK flip-flop and T flip-flop, we have to find what is the next state. For example, JA is equal to A bar plus B bar. So, 0 complement plus 0 complement, this is going to become 1. And Ka is, this is Ka. Ka is A plus B, that is 0. And TB is equal to, what's the TB value is given here? So, the TB is equal to A. Okay. So, the TB is equal to A. That is, whatever value is there, that is going to come here. Right, that's it. Okay, fine. So, now we have to find with this information what is the next state with the help of JK flip-flop truth table as well as T flip-flop truth table. For example, For a JK flip-flop, if input is 1, 0, I know that its output is 1 from the truth table. I know this information. So this is going to be equal to 1. Next one. For a T flip-flop, if input is equal to 0, what do you mean by that? The T flip-flop has only two conditions. If input is 0, Q of T plus 1 is equal to Q of T. If T flip-flop input is 1, it is going to toggle. As it is 0 here, so this particular previous output A, B, whatever is there here, that is going to remain same here. That is going to remain same. That's it. So from 0, 0, it is going to value of 1, 0. So I am going to put it like this. From 0, 0, this is going to 1, 0. This is the present state and this is the next state. Now, take this one as present state and we have to find out what is its next state. We have to find out the next state. So I am going to take this 1, 0 here. So in this case also, find out the flip-flop inputs of both JK and T flip-flop. With the help of truth tables, find out what is the next state. Let me calculate. JA is A bar plus B bar. That is 0 plus 1, it is going to be 1. Next, KA is A plus B. That is 1 plus 0, it is 1. Next, the TB value is same as your input A. That is, this is A. So keep it here. That's it. So that means for this particular one, so for this particular present state, at that point of time, the flip-flop inputs will be like this. Now we have to use JK flip-flop truth table information as well as T flip-flop input for analyzing this one. So first of all, the JA-KA is 1, 1. Because of this, whatever output it is having, that is going to toggle. I am putting the same mark here. You can understand, for 1, 1 condition in JK flip-flop, whatever output is there, that will toggle. Next one, let me change. For the next T input, it is equal to 1. I know that its corresponding output B is going to toggle. This is going to become equal to 1. That's it. So we have found that if the present state is 1, 0 for this sequence circuit, then the next state is 0, 1. So we have to keep analyzing, okay, and in this particular manner. Now we have to find out for this, what is the next state? That's the reason, bring this as the present state values here. Have a chain action. So keep a link in this manner. That's it. So again, I'm going to calculate what is the JA and KA value. JA, A bar 1 plus B bar 0. 1 plus 0 is 1. Next, KA is A plus B. This is also 1. Okay, next one. TB is equal to A, that is equal to 0. That is equal to 0. That's it. So now, based on these inputs, we need to find out now what is the output I am going to get. The first one is, it is 1, 1. That means its corresponding output 0 is going to toggle. Next, this input is 0. That means its corresponding output is going to remain same. That's it. Okay, so as it is 0, its corresponding output is remaining same. Means from 0, 1, it is going to 1, 1. That's it. Now, from 1, 1, what is the next state we have to find out? So take this 1, 1. And let us try to calculate what is the value of flip-flop inputs if the present state is like this. JA is A bar plus B bar, 0. KA is A plus B, that is 1 R with 1, it is 1. Next, TB is same as A, that is equal to 1. Then what will happen? Now look at this. For JK flip-flop, if input is 0, 1, immediately output is going to become 0. That's it. For T flip-flop, if input is 1, its corresponding output is going to toggle. Okay. So that is a simple description of the T flip-flop truth table. If input is 1, whatever its output is there, that is going to toggle. Means after 1, 1, it is again getting back to 0, 0. Means it is coming back to this place. So it is counting as 0, 2, 1, 3, okay, continuously. That is what we need to understand. Now let us look at the solution here. 0, 2, 1, 3, the correct option answer to this one is the D. D is the right answer for this. Okay, right. Now let's look at another problem. So some Boolean functions are given. So which of one of the following is a true one? Here you need to be very careful. Sometimes the question will be given as MCQ or sometimes the question is given as MSQ. MCQ means only one answer will be correct. But if it is MSQ, multiple answers will be correct. But here he has given which one of the following is true. That means only one will be the correct answer to this. So then how to simplify this? It's very simple. You have to apply little bit of your Boolean algebra laws, or else you can convert this totally into max terms or min terms, and then using the K-map we can simplify. That also you can do that. But I am going to show how to use the laws of Boolean algebra. For example, I am going to take the first one and third one. Sorry, this one. First one and third one. So these two we can combine by using distributive law, because if x bar plus y is equal to p, p plus z into p plus z bar is going to become p itself. So using this, the expression f is going to become in this fashion: x bar plus y. Okay, next x plus y bar z bar. Next, this term as it is. In this third term, I want to take z bar common in this one. I want to take z bar common. So this is going to become x bar y bar, x bar y, next xy. Right. You know that x bar y plus x bar y, x bar y bar plus x bar y, this will become equal to x bar. That's it. That will become equal to x bar. So f is equal to x bar plus y, x plus y bar plus z bar, x bar plus xy into z bar. That's it. Of course, I told you, you can convert it into max terms. By using K-map also we can solve it. But I am using laws of Boolean algebra. Okay, good. So this I have to use distributive law for this. Using distributive law, x bar plus xy will become x bar plus y. So this is f is equal to okay, so that is what we can understand. As you see, this term and this term, both of them are same. So x bar plus y into x bar plus y, that becomes x bar plus y. Write it only one time. And then this term you multiply with z bar. Z bar into z bar, this will become z bar. That's it. So this is going to become f is equal to x bar plus y, and here I am going to take z bar common. We know 1 plus anything is equal to 1. So I am left with f is equal to x bar plus y into z bar. So that is equal to x bar z bar and y z bar. This is the final expression. So once you apply laws of Boolean algebra in a careful manner, this is the final result we are going to obtain, and this is the correct answer to this. So the correct answer is A. That's it. This is the answer to this. So I have applied some distributive law most of the times, and then I come up with the final solution here. Okay, so next one is a simple one. A 10-bit ADC is having full scale of 10.23 volts when the digital output is this one. Okay, so that means if you give 10.23 volts as input, then output is equal to all ones. Okay, so that is the meaning of that is 3FF. The quantization error of the ADC in millivolts is, quantization error is nothing but the plus or minus step size divided by 2. So in this problem, we have to find out what is the step size. He is telling that for this particular input, this much output is coming here. And also, what is the step size of this A to D converter? So step size is given by the 10.23 volts divided by 2 power 10 minus 1. Okay, that is going to be the step size. And then quantization error is nothing but plus or minus step size by 2. So it is 10 millivolts. That's the reason the quantization error is plus or minus step size divided by 2, that is plus or minus 10 by 2, which is equal to plus or minus 5 millivolts. So for the given A to D converter, finally the step size will be 10 millivolts. Okay, that means that is the smallest change possible. That is the input change required so that the digital output is going to change. And from that we can calculate what is the quantization error, which is equal to 5 millivolts. So that is the answer to this question. In this problem, we are asked to find out canonical SOP expression implemented by this multiplexer among the given options. It is a straightforward. What I have to do is take the standard expression of a 4:1 multiplexer, and into that multiplexer expression, you have to substitute I0 to I3 values and S1 to S0. Be careful, I0 is given here and I3 is given here. I know for a 4:1 multiplexer, the standard expression is like this. Here the inputs are going to come I0, I1, I2, I3. So here the concept is simple. Substitute all the selection line values and inputs, convert them into minterms. That's what I have to do. So I'll do it step by step. S1 is equal to X. S1 is equal to X. So in place of S1 and S0, I will substitute X and Y. So F is equal to X bar, Y bar plus X bar, Y plus x y bar plus x y. Now take this input values and substitute into this correspondingly. Okay. So I naught is z bar plus w. I'll use some different representations. So I naught is z bar plus w. I1 is of course 0 and I2 is zw and I3 is zw bar. So I just need to expand it. So f is equal to x bar, y bar, z bar, okay, plus x bar, y bar, w plus 0. And this one is x, y bar, z, w. And this one x, y, z, w bar. That's it. You can see this one is already a minterm 1011. This is minterm number 11. This is also a minterm 1110. That is minterm number 14. So this I need not further expand it. So then these two terms I have to convert this into minterms. So I am going to write f is equal to x bar, y bar, z bar multiplied by w plus w bar plus this one x bar, y bar, w multiplied by z plus z bar, and of course minterm number 11 plus minterm number 14. That's it. So simply expand it. So f is going to become equal to x bar, y bar, z bar, w. So in which order we have to keep all the variables? It should be kept in this particular series x, y, z, w. This sequence we need to follow. So according to that, let me write it. Next one is x bar, y bar, z bar, w bar plus here x bar, y bar, z, w. Next one x bar, y bar, z bar, w plus minterm number 11 and minterm number 14. That's it. You can see x bar, y bar, z bar, w, it has come 2 times. So one you can cancel it because minterm 1 plus minterm 1, it is minterm 1 only. So you cancel it. Now I am going to convert that here. This is 0, 0, 0, 1, minterm number 1. Next 0, 0, 0, 0, minterm number 0. Next 0, 0, 1, 1, minterm number 3 and minterm number 11, minterm number 14. So f is equal to sigma m 0, 1, 3, 11, 14. That is the answer to this one. So the correct answer to this problem is A. This is the correct answer to this problem. Okay. So it is very simple. Use the standard expression of your multiplexer and substitute all the inputs and selection lines, then you will get the appropriate answer. Okay. Right. Next one is for a 4-bit flash type A to D converter where the full scale input voltage range is V, which of the following statement is or are true? You have to be careful here. Whenever it gives it as is or are, that means it is a MSQ question. It is a MSQ question. One option may be right or more than one option is right. So you have to carefully observe and give the answer. Okay, we know first and foremost 4-bit flash type ADC requires 2 power 4 minus 1, 15 comparators. And another thing is another thing you have to understand here is whenever the input change is by LSB value, that is VR by 2 power n, then the least significant bit is going to change. Okay? So that is the definition of your resolution. Resolution means what is the minimum change required at the input to make the LSB bit to change, LSB bit to toggle. If it is 0, it will become 1. If it is 1, it will become 0. Suppose if 0 volts is there, the output is all zeros. And when I give input as, this is your input. This is your input. So when I give the input as VR by 2 power n, then it is equal to, in this case, VR by 2 power 4, that is 16 volts, then output is going to change it to like this. As you can see, the LSB bit is going to toggle whenever my input is VR by 16. That is what you need to understand to answer to this question. Now let's look at one by one. The ADC requires 15 comparators. A is correct. Next one. The ADC requires one 4 to 2 priority encoder and 4 comparators. No, I told you now, if I am using 15 comparators totally here, 4 comparators is incorrect. So ADC requires only one 4 to 2 priority encoder and 4 comparators. This is incorrect. Next one is a change in the input of V by 16, it will change only LSB but not MSB. For MSB to change, we require a voltage change of V by 2. Okay, for MSB bit to change, we require voltage change of V by 2 volts. So this is incorrect and this one is the correct one. So the correct answer to this question is option A and D are correct. So these are the solutions for all the problems on your digital and microprocessors. In this problem, a 16-bit microprocessor is given having 20 address lines and 16 data lines. Apart from that, a 16 kilobyte memory is given. That means it is having totally 14 address lines and 8 data lines. So then it's telling that the memory should have the continuous memory location. So you cannot have the memory at the scattered location. It should be continuous one. That is the restriction here. Okay, and it should occupy only 16 kilobyte of memory space. That means you cannot have the duplication of the memory space. You should have only one memory space. That is what it is telling here. So which of the following statement is or correct with respect to the above design? So this is a MSQ question. Maybe one answer is correct, more than one statement is going to be correct one. Let us see one by one. So according to his description, first we should understand that this is your 16 kilobyte memory. So it should have a continuous memory locations here in this particular fashion given for that 16 kilobyte memory. It may be here, it may be here, or it may be here. It can be anywhere, but you should have a continuous allotment for that. Okay, number 2. Looking at the interfacing, according to its description, I have to say like this. A 16 kilobyte memory is going to have 2 power 14 into 8. That means it requires 14 address lines for internal access. This internal access lines, they will vary from all zeros to all ones. And 8 data lines, they are connected to the higher order data bus according to his given description. And of course, 20 minus 14, the remaining 6 address lines are connected to this address decoder. A19 to A14 is connected to the chip select of this particular memory. And you can see this is an active high chip select. It is a active high chip select. So this is how the interfacing is done. Now let us see out of the 4 statements, which of them is correct. Okay, that we have to see here. Right, first one. The above chip cannot be interfaced as the width of the data bus of the processor and the memory chip differs. We know the width of the microprocessor data bus is 16 and the width of the memory is only 8 bits. So can we interface them? Yes. So that's the reason this is your wrong statement. Why? Because even though microprocessor is having 16 data lines, memory is having 8 data lines, still they can be interfaced without any problem. So, that is not a correct statement. Number 2, the 16-byte kilo memory cannot be mapped with contiguous address locations with a starting address as 0F000H using only A9 to A14 for generating the chip select. So, unfortunately, if you start from the starting address, the memory is not going to come in a sequence. It will be scattered. Okay. For example, you take the starting address as 0F000H. Yeah. So, I'll take it here 0F000H. So, you know that for this particular memory A13 to A0, it varies from all zeros to all ones. 14 lines. Okay. So, this has to vary from all zeros to all ones in order to access each and every location in this memory of 16 kilobyte capacity. And then the A9 to A14, this is going to be meant for chip select. He told that the starting address is 0F00H. That means it is going to be in this fashion. Okay. So, that is the 20-bit address. Right. As I told you, 14 address lines are used for internal purpose. This is meant for internal access, memory internal access. And these lines are used for address decoding. Okay. These lines are meant for address decoding. As you can see now, if these lines are starting from 11000 to further it goes away, that means I am not going to get the values of internal memory locations at one place, they will be scattered. Okay. So, actually when it will come in a continuous memory location, only when if it starts from all zeros to all ones. If it starts with this value, ends with this value, then only the memory locations will come in sequence. But unfortunately, it is starting from 1 all zeros. That means we cannot expect the total memory locations as a contiguous one. So, that is the true statement. So, the second statement is a true statement. Coming to the third one, if the 16 kilobyte of memory chip is mapped with a starting address of 80000H, then the ending address will be 83FFH. Yeah, this is the correct statement. What's the reason? The offset of your 16 kilobyte memory, we can calculate it like this. So, starting from right side, you have to keep 14 ones and remaining 6 are zeros, 14 ones. Okay, I will keep it like this. And remaining thing are zeros. So, this will stand for 0, convert into hexadecimal, 3, F, 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 H. So, this is the offset of your 16 kilobyte memory. Then what is the statement is claiming here? Look at this. If the starting address is 840H, then the ending address is 83FFH. This is the true statement. The reason is this. Yeah, look at this. So, with this one, ending address is equal to starting address plus offset. That is 8000H plus what is this one? 03FFH. So this comes to 83FFFH. So for this memory, if the starting address is 80,000H, then its ending address is 83FFFH. So this is the correct statement. So if you go back to the statements here, the second one, C statement, is also correct. And coming to the last one here, if the active high chip select needed to map the 16 kilobyte memory with the starting address of F40H is given by this logic expression. This one is a wrong statement. The reason is this. Yeah, so let us look at why this is wrong. He has given that the starting address is F0000H. So that is equal to 111100000000000000. Right. So I told 14 lines, they are meant for internal access. So just leave it. And this is meant for address decoding. Okay, this is meant for address decoding. That's it. So that means only when A15 to A14 values are 111100, the chip has to be selected. That means it is absolute decoding. Okay, so only for that particular value of A19 to A14, the chip has to be selected. Okay, then only that can do that. That's the reason expression for CS is nothing but that is CS is equal to A19, A18, A17, A14. Okay, A19, A18, A17, A16, A15 complement, A14 complement. Yes. So as he given that its starting address has to be F000H, then we have to analyze it in this fashion. Whatever address lines we use it for internal access, you simply ignore them. And for the chip select, which are the address lines I am connecting? That is nothing but A19 to A14. And from the given address, I can find out that only when A19 to A14 is having these values, okay, these values, then only the chip must be selected. That's the reason the CS should be equal to this particular expression. Only when 111110, that is A15 complement is 1, A14 complement is 1, then only this chip will be selected. It is an absolute decoding. So based on this, let us assess what is the last statement. The active high chip select needed to map the 16K kilobyte memory with a starting address of this one is given by the logical expression A19, A18, A17, A16. The problem here is he is going for partial decoding. Actually, 6 address lines should be used for address decoder for the chip select, but out of 6, he is using only 4 of them. So this is incorrect. So the only correct answers for this particular problem is the B and C.